Okay, this is going to be the lesson video for differential equations, section 2.5 on solutions by substitutions. It turns out that sometimes you can do clever variable substitutions to convert a differential equation which is currently in a form you can't solve into an equation in the new variable that is a form that you can solve. And there's a number of these substitutions. In this section, we're going to pull two of them out to look at. One of them is some equations are in what's called the form of a Bernoulli equation, and there's a specific substitution that will work to convert that to a form we can solve. And the other one is, in the book, it's called reduction to separation of variables, but I think of it as a composite function, meaning one function inside of another. Under certain circumstances, when the differential equation right-hand side looks like that, we can do a specific substitution. And this will make sense when we actually go through it. So this is a fairly there's not a lot of slides here. I'm just going to do one example of each and then a third example here to show you how this works. Because essentially this is just a substitution. All right, so what is a Bernoulli form differential equation? Okay, a linear first order form requires, in standard form, we have dy dx plus some function of x as this coefficient times y. And then we have a right-hand side, which normally can be a function of x only. Okay, that would make it a linear differential equation which we could solve with an integrating factor, right? Okay, but if the right-hand side, if it's linear on the left, but the right-hand side function is a function of x, but then multiplied by y to a power where n is any real number, then this is called a Bernoulli equation form differential equation. And it turns out that if you make this symbol substitution, u is equal to y to 1 minus n, where n is this power that y is, and do the substitutions, you'll end up with a form which can be solved using the methods that we already know. So let's look at a specific example. Here we have a Bernoulli equation, okay, and it's almost in that standard form. Let's go ahead and put it in standard form, which is we'll divide everything by x, so we get dy dx plus 1 over xy equals xy squared, okay? If it weren't for this y squared out here, this would be a linear first order differential equation, which we could solve with an integrating factor. But because it has a y squared here, this is a Bernoulli equation form. And in this particular example, n is 2, okay? So what this is saying is this method says that means we can make a substitution. We're going to substitute the symbol u for y to the 1 minus n, which is going to be y to the 1 minus 2, which means u is going to be substituted as y to the negative 1 or 1 over y, okay? Now the problem is we have to also substitute the symbol dy dx, okay? So u is a function of y, but then y is a function of x. So we have to do some additional arithmetic over here. We're going to have to say, all right, what is the derivative of u with respect to x, the eventual independent variable? Using the chain rule from Calc 3, then we would have to say, well, first, u could be partial. There's a partial derivative of u with respect to x times dx, but then we have to add how much does u vary with respect to y times dy dx. And that gives us a term here that we can solve for, so we can substitute. Now, this particular substitution, u is not a function of x, but in the next one, u can be a function of x or y, or both. Okay, let's take a look at this then. The partial derivative of u with respect to x here, since there is no x in this u, this is, we write it this way, du dx is equal to 0, and then dx, of course, is 1. And then du dy would be the partial derivative of u with respect to y, which would be negative y to the negative 2, and then dy dx, which is what we're trying to solve for, which means du dx is equal to negative 1 over y squared dy dx, which means, therefore, that dy dx is equal to negative y squared du dx. Okay, so we go through this little exercise on the side with a substitution and take the chain rule derivative of that to find out what dy dx is so that we can substitute that for this. So we're going to put this in for that. So here's the substitution. At first, we just substitute that, negative y squared du dx. And then I've got the rest of my equation here, plus 1 over x y equals xy squared. The next thing we typically do is we divide both sides by, we divide everything by this negative y squared, because we want to put this back in standard form. So if you divide everything by negative y squared, then you're going to get that this is du dx. Okay, and this will become negative. We have 1 over x here, right? But then we have y over y squared, which is 1 over y. Okay, and then we'll have a negative here and an x, but the y squareds cancel out. Okay, so what that does is it effectively removes the part on the right-hand side, which was causing this to be not a linear first-order differential equation. And then there's one last substitution. This 1 over y here, 1 over y is equal to u. So that means I can now write this as du dx minus 1 over xu equals negative x. And now this is a linear differential equation, which means we can solve. Okay, since there's so few slides here, I'm going to go ahead now and solve this. But the main idea now is just that you can use this particular substitution here to cause this nonlinear equation to look like a linear equation here, but with a new independent or a new dependent variable. Okay, now the solution of this, in this case, we can do this with an integrating factor, right? This is my p of x is negative 1 over x. So that means my integrating factor would be e to the integral of negative 1 over x, right? Which is going to be e to the negative natural log of x, which is going to be, when you raise this up, e to the natural log of x to the negative 1, which is going to end up being x to the negative 1, which is 1 over x, right? So the integrating factor is 1 over x. And then we know that to solve this, we can say if we take the integrating factor times the dependent variable, that's equal to the antiderivative of the right-hand side times the integrating factor. Right? And so we're just saying 1 over xu is equal to the integral of negative 1 dx, which just ends up being negative x plus an integration constant. And when we multiply everything by x, we get u is equal to negative 1 plus c times x. Okay, so now we have a solution to our substituted differential equation. Okay, to finish this though, we then have to say, but wait a second, u was equal to 1 over y, so I must substitute this back out. 1 over y is what's equal to negative 1 plus cx. And so if you solve this, that means that y is equal to 1 over negative 1 plus cx. And this is the final general solution. Wait a second. Oh, I think I missed something here. Sorry, let me back up for a second. Yeah, let me go back up for just a second. When we get to this stage and we solve, I have 1 over xu equals the antiderivative of negative 1 dx, which is negative x plus c. Okay, so that's correct. However, so let me write this like this: 1 over xu equals negative x plus c. So what we need to do at this point is at this point substitute. So I made a mistake in the substitution. Since u is 1 over y, we're going to substitute that here. So I've got, let me move over here, 1 over x, and then the u is 1 over y equals negative x plus c. My mistake was when I multiplied both sides by x, this doesn't become 1 for some reason. I thought we were dividing. So when you multiply everything by x, you get 1 over y equals negative x squared plus cx. There we go. And that means that if you take the reciprocal of both sides, y is 1 over negative x squared plus cx. There we go. That's the general solution. Okay, so the main idea is this substitution. If you substitute this particular substitution and use the chain rule to find its derivative to solve for dy dx, you start by substituting out that. You divide out the leading coefficient. You substitute the portion that has the y, and then you'll get a new equation, which now it will be solvable using the techniques that we already have. Okay, that's the first of the two types of substitutions, and we use that whenever we have a linear equation, except that the form on the right is not just a function of x, it's a function of x times y to a power. Okay, the second one is called a reduction to separation of variables, but I think of it as a composite function because what it's saying is if we have something that would be separable, in other words, if you had dy dx equals a function where the function is, if we had the right-hand side was a function of x times a different function of y, we could move this to the other side and end up with 1 over gy dy equals f of x dx, and we could use integration of both parts because we can separate the variables. But that's if this is factorable, right? We can do our separation of variables technique. What if it isn't factorable, but you can write it as a composite function? So I'm going to indicate this is a composite function. In other words, the right-hand side can't be factored into x and y, but I can write it so that it's an outside function of an inside function, and the inside function can specifically be written as a numerical constant times x plus a numerical constant times y plus a numerical constant. Okay, if that's true, which is fairly rare, but if that does happen, then you can use the substitution u is equal to the inside function, and that will result in a separable differential equation. So let's see an example of how that would work. Let's say I have this differential equation. This is actually an initial value problem. So we have dy dx equals this, quantity negative 2x plus y squared minus 7. Okay, so that's not separable. I can't separate the x and y here into two factors for the entire right-hand side, right? But what this is suggesting is that since there's an inside function here, I can make my u, my symbol substitution, whatever's inside there. And then we're going to do the same thing we did on the Bernoulli one. We're going to calculate what du dx is. Okay, so what du dx is the partial derivative of u with respect to x times dx dx plus the partial derivative of u with respect to y times dy dx using the chain rule. So the partial derivative of u with respect to x, now u has x's and y's, so this partial derivative isn't 0 like it was in the Bernoulli case. This is going to end up being negative 2, and then dx is 1. And then the partial derivative of u with respect to y is 1, and then dy dx, which is what I want to solve for, so I have something to substitute. So now we have du dx equals negative 2 plus dy dx, and therefore dy dx is equal to du dx plus 2. Okay, so what I'm going to do is substitute for this over here. Okay, so let's start working on that. We get du dx plus 2 now is equal to this, which is u squared minus 7. Okay, and then if I move this 2 over here, I'll get du dx equals u squared minus 9. And this is a separable equation because I have y's and x's. So I should be able to gather each on each side. If you multiply both sides by dx and then divide both sides by this, you get 1 over u squared minus 9 du equals 1 times dx. So with this substitution, been able to convert this into a separable differential equation. So at this point, we can just use our normal methods, which is we're just going to take the integral of both sides to find the solution, right? Now on the left, I think we're going to have, we could use a vector or a form from a table. We could also use separation of variable or partial fraction expansion, which is what I'm going to do. You can show that, since this is 1 over u plus 3 times u minus 3, you can show in a partial fraction expansion that this is actually equal to 1/6 over u minus 3 plus negative 1/6 u plus 3. Okay, and so on the left-hand side, now that we're evaluating, we can say this is going to be the integral of 1/6 1 over u minus 3 du minus 1/6 integral of 1 over u plus 3 du. And on the right-hand side, it's the integral of 1 dx, right? So we'll end up getting 1/6 natural log of absolute value of u minus 3 minus 1/6 natural log of absolute value of u plus 3 equals x plus an integration constant. I'm going to identify that as constant number 1. We can use log properties to combine this. So this is going to be 1/6 natural log of u minus 3 over u plus 3 equals x plus c1. You can multiply everything by 6, which means natural log of u minus 3 over u plus 3 equals 6x plus some new constant. I'll call that c2, 6 times c1. And then if we did the e to the x on both sides, well, actually, yeah, let's do that. So I could just say that we know that the absolute value ends up being handled by the constants. We've seen this example before. So I'm just going to say that u minus 3 over u plus 3 is equal to e raised to that, which is e to the 6x plus c2, which is really e to the 6x times e to the c2, which is really just another constant times e to the 6x, right? All right, and then if I were to multiply this out, I would get that u minus 3 equals u plus 3 times c constant 3 e to the 6x, which is c3 e to the 6xu plus 3 times c3 e to the 6x. And then we can solve this for u. So there's a couple more steps in the middle, but you end up getting that u equals 3 times 1 plus c e to the 6x over 1 minus c e to the 6x. Okay, so here's a general solution with the substituted symbol. Okay, then the next thing we would want to do is substitute the u, and the u was negative 2x plus y. So we'll substitute, let me change colors here. This u is negative 2x plus y equals 3, 1 plus c e to the 6x over 1 minus c e to the 6x. Okay. And so when you solve for y, you get y equals 2x plus this 3, 1 plus c e to the 6x over 1 minus c e to the 6x. All right. And that's the general solution back in the original equation. Now, this particular one had an initial condition when x is 0, y is 0. So we should be able to use that now to establish the constant. So finally, saying that, okay, when y is 0, or when x is 0, y is 0, if I plug 0 in for the x and the y, I have, let's see, this is 1 minus, this is supposed to be a c here, sorry, and then c, and then e to the, if you plug a 0 in here, this becomes 0, 1 minus c e to the 0. So we get 0 equals 3 times 1 minus c over 1 minus c, right? Okay, I'm making a lot of mistakes here. There's a plus on the top. That means, therefore, that the only way that that is true is if the numerator is 0. And if we have a fraction equals 0, the numerator is 0. So I'm solving for 3, 1 plus c equals 0, which means 1 plus c has to equal 0. So that means c has to equal negative 1. Okay, and that means that we can write now our particular solution. It's y equals 2x plus 3, 1 plus, and then c, but c is negative 1. So I'm going to change this to minus and then e to the 6th x. I'm substituting negative 1 in for these two c's here, over 1 plus e to the negative, or e to the 6x. This is the particular solution for that particular initial condition. All right, but the important point is if you have the right-hand side as a composite function, something clearly inside of another function, just make u the inside function, and sometimes you'll, when you substitute and do the 3D Calc 3 chain rule, you'll be able to convert this into something which you can use separation of variables on. All right, and then I just have one more example here. So let's take a look at this last one. It says dy dx minus y is e to the x y squared. So this is in standard form. It would be linear, except for this y squared over here, because this is a function of x, negative 1 is a function of x. So this is a Bernoulli form with n equal 2. And so that means our substitution is going to be u is y minus, or y to the 1 minus n, so 1 minus 2, so y to the negative 1, so u equals 1 over y. Okay, and then to figure out the dy dx, we'll do du dx, chain rule, partial u with respect to x times dx dx, plus partial u with respect to y times dy dx. Okay, there is no x in this u for Bernoulli, so that's 0. This is 1, but this is negative y to the negative 2 dy dx. So like that last example, we have that du dx is negative 1 over y squared dy dx, which means dy dx is equal to negative y squared du dx. Okay, so we will have something to substitute for this dy dx here, and we'll do that in the next step. So the next step is we put negative y squared du dx in here, and then we divide everything on both sides by the leading term here to put it back in standard form. And we end up getting du dx, and then the minus minus cancels to become a plus, and y over y squared is 1 over y. And then these cancel except becoming negative, right? And then finally, the last substitution is 1 over y is u. So we have du dx plus u equals negative e to the x. So this is a first order linear differential equation. We can solve this one with an integrating factor. So now that we've converted it, let's solve it. Okay, and I'm going to do that with an integrating factor. The integrating factor is e to the integral of this one right here, dx. So it's going to be e to the x, right, the integrating factor. So the idea then is the left-hand side is the derivative of the integrating factor times the independent or the dependent variable is equal to the right-hand side times the integrating factor. Okay, so we end up taking the derivative over here, and we get the integrating factor times the y variable, in this case is u, is equal to the integral of whatever this is, which is going to be e negative e to the x plus x, which is 2x dx. So that antiderivative is divided by the constant, so negative 1/2 e to the 2x plus an integrating factor here. And so I can now substitute what u is. U was 1 over y. So I've got, let's go back to blue here. We're going back to the original. So e to the x 1 over y is equal to negative 1/2 e to the 2x plus the integrating factor, or the integration constant. And so then if I divide everything by e to the y, I get 1 over y equals negative 1/2 e to the 2x divided by e to the x is just e to the 1x. Okay, and then I've got the c times e to the negative x, because it's the same as dividing by e to the positive x. And therefore, y is 1 over all of this. So it's going to be 1 over negative 1/2 e to the x plus some constant e to the negative x. This is the general solution. And if we were given an initial condition, we can plug in x and y and solve for c. All right. think that's all I have, and you should, with that, be able to attempt the homework for section 2.5.